So in this video we're looking at definite integrals. So here's our definition of a definite integral. If f is defined on the closed interval from a to b and the limit of Riemann sums over the partitions delta exists, now this is that Riemann sum, the limit of the Riemann sums over the partitions, the norm going to 0. If this exists as described, then f is said to be integrable on the closed interval from a to b, and the limit is denoted by putting these little a and b's on our integral symbol. We call this the definite integral of f from a to b. Now the number a on the bottom is called the lower limit of integration, it's the smaller value, and the number b is the upper limit of integration, the bigger value. Okay, so we're talking about on an interval from a to b. Now, though Riemann sums were defined for functions with very few restrictions, a sufficient condition for a function to be integrable on a to b is that it's continuous on that interval. So, Theorem 4.4 basically just tells us that continuity implies integrability, okay? So, if a function is continuous on the closed interval from a to b, then f is integrable on that closed function, or that closed interval from a to b. Therefore, the integral from a to b of f of x dx does exist. Now, that being said, let's look at this function. We want to evaluate the definite integral of 2x dx from -2 to 1. So for us to use this limit definition, or this definite integral definition, we need to know, is the function continuous on that closed interval? So from -2 to 1, is 2x continuous? Absolutely, it's continuous on the entire number line, so we know we can use this definition. So this is what we're going to do. We are going to say that this integral is equal to the limit as the norm approaches 0 of the sum of FCI delta xi. Now, this is a Riemann sum, but we're actually going to use one of our upper or lower limits. We're going to pick our delta x so that it's a normal interval, right? It's regular. So we're going to say it's b minus a over n, which in this case we know that this is equal to a, this is equal to b, right? So we can say this is 1 minus -2 over n, or 3 over n. Now, I want you to look at your, let's think about this function. Something like this. So we're talking about this region here, okay? Now, and I don't even care, you know what, I don't even care about the graph. I just want to look at my x values, because this is what I need. This CI is what I need. So let's look at our intervals. So if we start at -2 and go to 1, and we've got our intervals every 3n. So this distance is 3 over n, this distance is 3 over n, this distance is 3 over n, right? It's a regular subinterval. So this is -2, but this is -2 plus 3 over n. This one is -2 plus 2 times 3 over n, right? This one is -2 plus 3 times 3 over n. So notice, what if we use this, we think about this as being, you know, these partitions, and we use the right endpoint. The right endpoint is just -2 plus I, right? So, or I delta x, I3n. So I know that CI will just be -2 plus I times our delta x. Now we could use the left endpoint, but the problem with using the left endpoint would be that this is for the right. For the left endpoint, CI would be -2 plus I minus 1 3 over n, right? Because I have to start with 0, but I know I always has to be 1 first, so 1 minus 1 is 0. So this is going to give us a little more complicated CI, so we don't want to use it. We always want to use the one that's going to be the easiest for us to get our values. So we're going to use this CI. So we want to find, all right, the limit as Now, since it's the limit of the norm approaching 0, that's the equivalent of n approaching infinity, right? We talked about that. So if n is approaching infinity of the sum from I equals 1 to n of f of ci, so our function is 2x, so 2x, so 2 times whatever the x value is, which is negative 2 plus 3i over n, and then times delta xi, which in this case is delta x, or just 3 over n. So this gives us the limit as n approaches infinity, the sum of 6 over n times negative 2 plus 3i over n. So let's go ahead and pull that. You know what? I'm going to take the limit off for a second, and we're just gonna be working on the sum. So I know I can pull that 6 over n out. I equals 1 to n, and this is going to give us negative 2 plus 3 over n I. I don't have that. Don't need that. So we know we can go ahead and do this. Negative 2 is going to give me negative 2n. That's the summation formula, right? Plus 3n times I, which is n times n plus 1 over 2. So this is going to give us negative 12 n over n plus 18 over n squared times n squared plus n over 2, or negative 12 plus 9, right? 18n squared times n squared. The n squareds will cancel out. 18 divided by 2 is 9. Plus 18 9 over n. So if I'm going to take the limit, so the limit as n approaches infinity of negative 12 plus 9 plus 9 over n, that goes to 0. I get negative 12 plus 9, which is just negative 3. So that's the value of that definite integral. Now, because this definite integral is negative, okay, see how we've got a negative 3? It doesn't represent the area of the region shown, okay? So if you think about this, this is what the actual picture would look like. Notice that some of our region is in the negative range. Some is in our positive range. Now, it can't be the area, the entire area, because you can't have a negative area. But definite integrals can be positive, they can be negative, they can be 0. Now, for the definite integral to be interpreted as an area, the function has to be continuous and non-negative. Okay, that's the only way for us to think of it as being the absolute area being bounded by the x-axis and those upper and lower bounds. And we can look at it in this theorem. This is the definite integral as the area of a region theorem. So if f is continuous and non-negative, then the area of the region bounded by the graph of f, the x-axis, and those vertical lines x equals a and x equals b is given as the definite integral of f of x from a to b. This only works as long as we are above the x-axis the whole time and we are bound by a and b. Now, as an example of Theorem 4.5, we can consider this region bounded by the graph of 4x minus x squared, the x-axis. It's automatically bounded by 0 and 4 because that's where it crosses the x-axis, okay? Now, because f is continuous and non-negative on the closed interval from 0 to 4, then we can just write the area of that region as strictly the definite integral of that function from 0 to 4. And this is one of the main ways we're going to use integration, is by doing the area under a curve. Now, you can evaluate definite integrals in 3 ways. There's only 2 ways that we've done right now, but we're going to get to a 3rd way. But right now, we'll say 2 ways. You can either use that limit definition, or you can check to see whether it might actually represent some area of a common geometric region, something like a rectangle or a triangle, or even a half circle. Okay, so let's look at a couple examples where we can actually use geometry or geometric shapes to determine what the definite integral is. So here, we've got the definite integral of 4 from 1 to 3. So let's think about what this graph looks like. The graph of y equals 4, 1, 2, 3, 4, is just a straight horizontal line. If we're bounding between 1 and 3, then this is just a rectangle, right? It has an area, or a base of 2, a height of 4, so we know that has to equal 8. Right? Base times height. Length times width. Okay? What about here? We've got x plus 2 from 0 to 3. Once again, 1, 2, 3, 4, 5, 6, 0, 1, 2, 3. So, if I plug in 3 plus 2 is 5, so 3, 1, 2, 3, 4, 5. I know it crosses the axis at 2. So we have this. But notice I could break this up into 2 by 3, and then here I've got a 3, 1, 2, 3. So I know I've got a triangle that's got a base and a height. I've got a rectangle that's got a base and a height. So my area is equal to 2 times 3 plus 1/2 base times height, which is going to give us 6 plus 9/2, or 12/2 plus 9/2, which would be 21/2. All right? What about here? Here we've got the square root of 4 minus x squared from -2 to 2. If I were to graph that, it just looks like this. It's the area under that curve. All right, so this is a area equals pi r squared, but it's only half of it, right? So the area of this one is 1/2 pi r squared, but what's r? In this case, r is 2, so our area equals 2 pi. All right, now the variable of integration, indefinite integral, is sometimes called a dummy variable. We call a lot of things dummy variables because it really doesn't matter what they are. It's just like the summation. You can do it over any variable, right? It doesn't have to be I, it could be J, it could be K, it could be B, it could be smiley face, it could be, whatever. We call it a dummy variable because it can be replaced by any other variable without changing the value of the integral. Okay, so look at these two. The integral of x plus 2 dx from 0 to 3 and t plus 2 dt from 0 to 3 are exactly the same. They have the exact same value because the variable is the only thing that's changed. It would also be 0 to 3 of smiley face plus 2 d smiley face. Right? All right, if you have any questions about definite integrals, just shoot me a reminder or ask questions in class.